looks like we're about there. Welcome back, everybody. Before we get started, I'm happy to take any questions folks might have. Is there any questions so far? Yeah, go ahead.
Could we go over 25?
Yeah, I'd be happy to. How does number 25 go?
The equation is y equals x sine of x from 0 to 2 pi with 4 subintervals in 0.
Okay, so we're going to, this is a problem of find the length of this curve, right? And approximate it Simpson's rule. Okay, so find the length of this curve. Well, we're not going to find the exact length. We're going to approximate it because this is a very terrible integral. So let's say instead of finding the length, let's say find the approximate length of this curve using S4, or like for S4 we mean just Simpson's rule with n is equal to 4 subintervals. So this is an interesting problem because if we want to approximate the integral, say, from 0 to 2 pi of x sine x dx with Simpson's rule, it wouldn't be the right thing. We'd just be approximating the area under the curve. We wouldn't be approximating the actual arc length. So in order to get through this problem, we cannot do this, sadly. So if you wrote that down in your notes, sorry, either erase it or line it through. What we have to do is start with the definition of the arc length function, which says the length of this curve will be the definite integral from 0 to 2 pi of the square root of 1 plus dy dx squared dx. So we have to start with that format there. So the next steps to take are figure out what the actual integrand is. Once we have the integrand, then we'll apply Simpson's rule if n is equal to 4 on that function. So it starts off as just about every single problem starts off in sections 8.1, 8.2. We take the function, compute its derivative, and square the result. So that's where we're at so far. Let's do, say, the algebra over here. Y is equal to x sine x. And the first conflict we have when we take the derivative is we have a bona fide product rule. So we have to take the derivative of one function, copy the other, add to that the result of the derivative of the other function, copy the other one. So in other words, dy dx would be equal to, I typically take the derivative of the first function first, but any order is completely okay. So if you take the derivative of x, we would have 1 times sine x plus copy x, multiply by the derivative of sine, and we'll get a cosine x. And that's our derivative by the good old product rule. Any questions with that step? Okay, really feels like we hardly do product rules and quotient rules in this class, so it's always good to brush off the dust on those and practice with these kinds of problems. Next thing we are going to do is square that entire result. So we're going to take sine x plus x cosine x, multiplying by itself. So sine x plus x cosine x for the second factor. And this will turn into sine squared x. Multiplying here to here will give us sine x cosine x times x 2 times when we multiply here and here again. So 2 copies of x sine x cosine x. Then finally we multiply here to here to get an x squared cosine squared x. Tragically, nothing really simplifies there. We almost have sine squared plus cosine squared, but the x squared is blocking us. One thing we can do is say that 2 sine x cosine x is a double angle formula, which gives you sine of 2x. And if you didn't do that in your homework, it's totally fine. The only real reason to do that is slightly less writing when we get to the next steps. So that's a tiny, tiny simplification, giving us sine squared x plus x. Then 2 sine x cosine x by this identity gives us x times sine 2x plus x squared cosine squared x. Then that's the derivative squared. Any questions to that step? It's not the prettiest looking thing, is it? But it is what it is. And when we take the square root of this thing, nothing is really going to simplify there. We can't break a root across addition, only products. And there doesn't seem to be any clear way to factor this from what I can see. So instead, we could just immediately come back over here and say, well, the arc length function from 0 to 2 pi is now the square root of that whole mess, which was the derivative squared, and add 1 to it. So slightly messier. We get sine squared x plus x sine 2x plus x squared cosine squared x plus 1. And we're going to have to extend that square root sign with a dx. So finally, once we get to that format, we now know what the integrand is, and we know what the type of integral we're going to approximate with Simpson's rule for subintervals. Any questions to that step so far?
Do we have to FOIL it out like that, or can we just leave it sine x plus x cosine x squared?
Actually, that might have been the wiser decision because it's less writing. Foiling it out was, for me, just to explore to see if anything simplified there. I have got nothing. So I think you would have been better off to just say, inside the root, like you said, sine x plus x cosine x squared, then just add 1. And it would be, in fact, a lot better looking than what I did. So that would be the best route to go so far. Other questions with that to this step? Okay, then the homework said to approximate with n is equal to 10. If you did that, that's completely fine. I mean, it is a lot more busy work, essentially. So n is set to 4 is just to give us not as much worry to write out all the parts of this. So now let's go and say the arc length L is going to be approximately equal to S4, which by formula is a delta x divided by 3, multiplying f of x naught, 4 f at x sub 1, 2 f at x sub 2, 4 f at x sub 3. So the pattern goes for coefficients 1, 4, 2, 4, then finally it has to end at a coefficient 1, and that would be the f of x sub 4. So there it is. Next thing we have to do is do as much of the evaluations as we'd like. We don't want to write out the full details like we did in the very last chapter, where the focus was learning the Simpson's rule. We just want to get through the problem as fast as possible. So this is what I would do as my very next steps here. I would first calculate delta x as usual. Delta x will be the upper limit of integration, 2 pi, minus the lower limit. It doesn't always have to be 0, so keep in mind it could have been, say, pi. Divide by the number of subintervals, which was 4. So it's 2 pi divided by 4, or pi divided by 2. Then we know the first endpoint of the intervals is x naught, set equal to the lower limit of integration, which is 0. And we get all the other values by adding pi over 2. So x sub 1 is pi over 2, and then so on, until we end up at 2 pi. So we've got this setup ready to evaluate, and we can write that delta x, which was pi divided by 2, will be divided by 3. That gives us a pi divided by 6. Then we can go inside the function and write f of 0 plus 4, f at pi over 2, plus 2, add pi over 2 to this, so we'll get pi, or 2 pi over 2, plus 4, f at 3 pi over 2, plus f at 4 pi over 2, which reduces to 2 pi. So we've got the function evaluations in there. Well, we haven't quite evaluated them, and we can, and a lot of things would simplify, but this is still a tremendous amount of writing. So for the purpose of, say, homework and exam number 2, let's introduce a bit of a shortcut to say you can abuse a little device to say here that the arc length is approximately equal to Simpson's rule with 4 subintervals, which becomes this. And instead of writing out all of that stuff, which is busy work, I would add on my paper where f of x itself, just tell me what your f of x function is. It's definitely not x sine x. It comes from over here. And let's borrow that idea where we could have just taken this plus 1. F of x is sine x plus x cosine x, all squared, plus 1, and it's also under the root. So if you tell me exactly what the function is here, the correct integrand, then I think that would be a sufficient shorthand for the entire answer. For those of you that are brave or possibly have a computer, which is the best way to go, you can approximate this thing, and let me see what it should come out to, in case we're curious and want to compare notes. No claim that this is perfect, because I did use a handheld calculator on this, and I got about 13.231. This right here would be optional. So if you stopped right here on homework, that'd be okay with me, especially if you're taking an exam. Stopping right there would be perfectly fine. Just make sure that you do this portion right here. As long as I know exactly that you know what the integrand is, I'd be happy. Any questions with that problem? Okay, it's a nice problem to have, since if we're calculating arc lengths and surface areas of surfaces of revolution, then a lot of times those integrals are just completely unapproachable, and we are forced to use numerical methods. So this is a way to get through that. But any other questions folks would like to discuss before we start today? Okay, and this could have been, say, on exam 2, a problem that you would get, or it could have been the surface area, where the only difference is 2 pi times the radius, whether that's the variable of the entire function, but the work is going to be the same. Trickiest part is getting the right integrand. Let's move on next to section 8.3, where we discussed how to get center of mass for certain regions, which are not point masses. We give it a fun, fancy name called centroid, but if you think center of mass every time you hear centroid, that'd be completely appropriate. Then we mentioned there are certain situations where it gets a little bit more interesting when we're bounding a region by 2 curves. We didn't quite get a chance to do that problem, so that's what we ought to do very next. Any questions then before we start those last couple problems in 8.3? Okay, so the only problem we didn't quite get to on 8.3, I believe, is this one right here. So let's take a look at something that goes along those lines. We have a region bounded by a set of curves. Those curves are going to be on this problem, y equals square root of x, and y equals x squared. So the full statement of the problem would say, to find the centroid for the region bounded by the curves y is equal to the square root of x, and y is equal to x squared. So that's our situation, and for an exam problem, a sketch would be provided on the actual exam itself. As a homework problem, this is all we get, but it's a really good idea to actually sketch that region. In order to sketch that region, the trouble is nothing in the problem told us the actual domain over x that we're going to be doing all the integration. So there's a couple ways to get that. One thing we could do is set root x equal to x squared and just solve the equation. Another approach would be, let's just sketch the curves and see if we can tell where they would reasonably intersect. That's probably what I would do. Let's skip solving the equation unless we're unsure where the points of intersection actually would be. So starting with square root of x, we'll have a value at the origin. At 1, square root of x is 1, so we have a point here, and at 2, 3, 4, the square root evaluates to 2. So the sketch of the square root looks about like that. We're not going to need the entire curve, more likely than not, so we're eventually going to delete some of it, but at least we know some region is going to be bounded using this curve. Now we throw in the x squared curve, though we have to label these as we go. This is y equals root x, and the sketch of x squared once again starts at the origin. Then if we input 1 into y equals x squared, we get back to 1. So we have a point of intersection there as well. Now let's do maybe one more point. At 2, if we square 2 in this function, we'd be at height 4. So we have a value way up here, and the graph of the curve would look about like that. So this is the y equals x squared curve. So we don't need the entire sketches. Once again, we're looking for a bounded region. What would you say the bounded region is? Where would it actually be in the sketch?
tiny, tiny piece at the very bottom.
Yeah, it'd be exactly this little piece right there. So we can do a whole lot of deleting. Let's delete all the way back to this point here. And also recall which curve was which. That was probably a little bit aggressive for deleting. The bottom curve was the square root function. And the top curve is the squaring function. Okay, so we want the centroid of that region. One thing that's kind of tricky about this is if you were to say draw a line, y is equal to x, it looks like we have symmetry about this line, which is kind of neat. So you might guess halfway from here to here would be exactly the centroid. It turns out that is not the case. It's just very hard to draw these curves perfectly by hand. There's a slightly more mass on the left end from 0 to 1/2 than there is from 1/2 to 1. So the centroid is going to be somewhere slightly left down that line, but we'll see about where it is. Any questions before we start then with the setup of the problem? Okay, first thing we have to do is, for finding the centroid of this region, we're imagining that this is just a two-dimensional top view of some weird looking plate. The book likes to call this a lamina, so it's something with the exact same thickness and a uniform density all throughout. So we want to know where would that balance, and the first thing that's important in those formulas is the area. So we want to find the area of this region that's bounded by the curves. The integration will go from 0 to 1, since we have a point of intersection at 0 when the curve is bound, up to 1. The next thing we take is the upper curve, x squared, minus the lower curve, square root of x. Or hang on, I think I got those curves backwards. Does that look backwards to folks? That would be problematic if you calculated this, but in a sense that's actually okay. If I calculate this as the area, well, that's a false equation. I would really be calculating negative area. So if I got a negative result, it would tell me right away, well, those curves are backwards and I need to fix it. And I would just immediately state the true area is the negation of what I would get over here. But while we're at it, let's just fix this. Let's call this the root of x as it is. Bottom curve is, in fact, x squared. I knew I deleted those curves too fast. So now, over here, it's root x minus x squared dx. Then that's just an ordinary integral, and we can immediately get the antiderivatives. This is now positive area. The antiderivative of root x is x to the power of 3/2 multiplied by 2/3. Minus antiderivative of x squared is x cubed divided by 3. I'll evaluate as x ranges from 0 to 1. So the antiderivative is complete. When we input 1, we get 2/3 minus 1/3, and 0 wipes out everything. So it's a nice problem rigged to just go a bit quicker than normal. Probably a good exam type problem. We now have total area exactly 1/3. Now we're ready for the next portion. Any questions to that step so far? These are interesting problems because if you're going to find a centroid, really it's 3 definite integral problems duct taped together. Sometimes the integrals are really immediate. The total area integral usually doesn't need any kind of fancy techniques. And sometimes you can skip out of other integrals by using symmetry. We just have to be very careful about the symmetry when we decide to do that, as we mentioned last class. But now let's go to x bar, the first coordinate of the centroid. So x bar is first the reciprocal of the total area, and that's why we calculated that first. Multiplying a definite integral from 0 to 1, and our formulas say to take x times the top curve, which is root x. If the bottom curve is y equals 0, then we would just stop. However, the bottom curve is, oh hang on, yes, bottom curve is x squared, so we take root x minus x squared. In other words, the same exact quantity here, we're just multiplying it by x. So the definite integral would look like that. But then once again, this is not too terrible. There's an extra step where if you want to find the antiderivative, we'll just multiply first by the distributive law. First reciprocal of area is reciprocal of 1/3, so you can take care of that next step. We have the definite integral from 0 to 1, and this is x power 1/2, so x power 2/2 gives us x to the power of 3/2 minus x cubed. So we're ready to find the antiderivative of those two terms and evaluate. Does that look all right so far to folks? Okay, once we get an answer, we'll be able to go up here and see if that x-coordinate really makes sense. It should be slightly less than 0.5. I would have guessed 0.5 exactly if that was my hand-drawn sketch, but a good sketch you'd see on the exam would show you that there's more mass to the left. So something slightly to the left of 0.5 is what we're expecting. So let's find out if that indeed happens. First reciprocal of a third gives us 3, and we're going to get the antiderivative of x to the power 3 halves, add 2 over 2 for 5 halves, and multiply by the reciprocal 2/5. Then we just do it again. This will be x power 4, multiply by the reciprocal of that power, which is a 4th, and everything is evaluated from 0 to 1. Does that look all right to that step, folks? Okay, the evaluations go really, really rapid thanks to the 0 in there, and the 1 as well. So we have 3 times the result of 2/5 minus 1/4. That's evaluating at 1, and evaluation at 0 wipes out everything, which is terrific. So it just boils down to that computation. Let's just work it out by hand to see what we have here. If this was an exam problem and you did stop at this point, that would be okay. So we have altogether, say 8 minus 5/20 multiplied by 3. So this is 3 times 3/20 for a 9/20 altogether. And notice if it was 10/20, that'd be perfectly a half. So 9/20 is ever so slightly to the left of 1/2. So this is where we're at so far. We have this line y is equal to x, and we found a point slightly less than 1/2, and I would guess it's directly on that line, y is equal to x. Would you folks make that same guess? Does that seem logical? That's actually cool then, because if we notice a symmetry about the line y is equal to x, notice we just said x bar is 9/20. So input x bar here as a particular value of x, and it immediately will tell you y bar is also 9/20 by that symmetry. So if you did that on, say, an exam, that would be terrific. Homework, terrific as well. But if you were trying to practice the formulas, we just cheated ourselves on doing y bar. Is that all right with folks if we do it anyway? Okay, let's verify if there really is a specific symmetry and we really get 9/20 by calculating this. So let's check that out. But for emphasis, if you skipped this next computation because you notice symmetry, you're free to just state y bar is 9/20 without explanation. I'll assume that you just looked at the symmetry already built into the problem and were able to tell the coordinate. But if we work this out by formula, it's really not too bad, but it is work. We have to write that y bar is, once again, the reciprocal of the area, so we do that same computation. It's still a definite integral from 0 to 1. Then we know from formulas that we would take, ordinarily, a half of, let's just write this as a formula first, f of x, and square the result. Then on all the problems that we did last class, the second curve was 0. So you could say minus 0 squared and just be done. So the prior formulas reduced to what we were doing last class. Now this will become equal to g of x squared. We'll think of this as the g function. So this is our f of x and g of x that we calculated the area. In the x-coordinate of the centroid, we took x times f of x minus g of x. However, for the second coordinate, we take a half of the function f of x squared minus the function of g of x squared. And what's very interesting about that formula is a very, very common mistake on homeworks, and even on exams, is to put the power 2 out there. Please don't do that in your notes. That's very, very incorrect, and it's going to make the integral worse or possibly not even approachable. So the power of 2 must go here, which looks interesting. It looks like someone FOILed things incorrectly. It's just a feature of the derivation we would have to go to that would give us that strange looking result. But in any case, we can now evaluate to say that this is reciprocal of total area, which is a third. Let's take out the half while we're at it. Multiplying the definite integral from 0 to 1 of f of x is referring to the top function in the graph, the square root of x. So we square that and just get x. Minus g of x squared, so that would be x squared squared for x power 4 dx. Then that's pretty much it. So it's not too bad of a computation either, even if we went right through it. So let's do the usual thing. The reciprocal of a third gives us 3. Multiplied by a half, we're up to a 3 halves. Antiderivative here will give us x squared times a half minus, for the second term, it'll be x to the power 5 times a fifth. All of it evaluated from 0 to 1. So we're pretty much there. And there's a bit of a drama in this problem because we're expecting exactly 9/20ths. If we do not get exactly 9/20ths, everything on the chalkboard looks like a complete lie. So let's see if it works out. So we have 3 halves multiplying, insert 1 into both of these functions, and it's a half minus a fifth. Then once again, the evaluation at 0 wipes everything out, so we can stop there. Then this becomes 3 halves, multiplies 5 to here, will give us 5 minus 2 to here, 2. Multiply the denominators, produces the least common denominator of 10. So we're up to 3 halves times 3 tenths, which gives us miraculously a 9/20ths. So our intuition worked out this time, but we should be very, very careful about symmetry because a lot of the problems don't have those kinds of features. That's kind of a neat one because we have a symmetry about a non-standard line y equals x. Any questions about that problem so far? Okay, so that tells us the centroid should be precisely here, with y bar at 9/20ths and x bar of 9/20ths. It's really closer to a half, but it's hard to draw without zooming in on that further, so it's a bit exaggerated. So that's how you can get the centroid of region bounded by a pair of curves. The adjustments are, we have to find the top curve and the bottom curve. And if we guess wrong, then the area will tell us immediately. Then we take x, and the new part is we also subtract the bottom curve here, and the new feature on this portion is subtracting the square of the bottom curve again. Aside from that, everything else proceeds exactly as before. And if the second curve was y is equal to 0, you could have inputted that into all 3 computations, and it reduces to the formulas we had been using before. Any questions with those computations so far? Okay, I guess I have one question for folks, which should we do one more, which is harder, or would you folks like to start chapter 9? Totally your call this time. Harder version of this one, or totally new topic?
Let's do one more.
One more? That sound all right to folks? All right, let's do one more. So this time, it's almost a review of certain antiderivatives, so it makes for an interesting problem. We have curves given by y is equal to the natural logarithm of x. Second curve is y is equal to the linear function, x minus 1. Then the remaining curves are just the straight line segments. X is equal to 1, and x is equal to 3. So this is a nicer problem since we don't have to worry about where the points might intersect. We don't have to worry about solving the equations. X specifically ranges from 1 to 3. So very next, let's throw in the sketch of this. The natural logarithm function at x is equal to 1 will always have value 0. So this is a nice thing to always have in the back of your mind because natural log 1 equals 0 and the natural log of e equals 1 are just very common things to throw on exams to rig the problems and make computations fast. So next, if we go off to 3, note that this is a e, which is about 2.7-ish, and natural log of e would have been 1. So that means natural log at 3 is just a little bit higher than 1. So I'll put the point about here. It's not a perfect sketch so far, but it's about right. So the graph of the natural logarithm curve would look about like this on that domain. Then if we just plot y is equal to x minus 1, For this function, if we input 1, we would have a value of 0. Oh, but first, let me say what function this one was, lest I forget. So that curve is natural log x. Next, we take the second curve, input 1 here, and we get a value of 0. So we have a point of intersection. If we input 3 into this curve, we would get a value of 2. So let me replace that description. Natural log x is now promoted to the bottom curve. I guess that's a demotion. And we have a height of 2 on that curve when x is 3. So the sketch looks about like this. There is separation there, but the width of the chalk is making it hard to sketch. And this would be our region. So we want the centroid of that thing, whatever that would be. Any questions then with the setup so far? Okay, so now let's call this y equals x minus 1. If we were to visually estimate the centroid, I would probably just throw it somewhere in here. Possibly folks would jitter that a little bit into a better place, or move it quite a lot depending on if you're really good at eyeballing centroids. But it's good to just put an estimation of it, possibly on your exam, just to see if the values we get are about right. So now we're ready to start. Any questions before we go through the 3 integrals? Okay, terrible feature about this problem is there is absolutely no useful symmetries there. So we just have to walk through all 3 parts. There's no real shortcuts. While doing that, we're going to do some interesting integrals, but it's good review and good things to mention when you see these sort of things on exams as well. So first, we want the total area of that highlighted region, which will be the definite integral as we go from 1 to 3. We must take the correct top curve, which is x minus 1, and subtract the bottom curve, which is the natural log of x. So this time, that is our total area integral. It's not too bad, except when we go to term-by-term anti-differentiation, we'll get x squared divided by 2 minus x minus the antiderivative of the natural logarithm of x. So that already is something we ought to work out on Scratch. Let's solve that thing so that we can input all antiderivatives in one go. I think that'd be probably the most efficient way to get through this one, rather than carrying the entire antiderivative for total area line by line with that as an antiderivative. Could take a lot of copying. But one question that we ought to ask is, anyone happen to know that antiderivative? We've done it a couple times in class. I ask because if you do happen to know that antiderivative, that's fair game. If you see the antiderivative of natural log x on an exam or homework assignment, you're completely fine to state that antiderivative and move on, no work shown. Only because these show up a lot, and I'm not going to expect you to do the integration by parts every single time it shows up. But maybe one more time? Does that sound right to folks? Okay, so for the sake of reviewing the technique, let's work this out using integration by parts once more. So let's say u is equal to the natural logarithm of x. Then the differential of u would be 1 over x dx. Next, we start with the differential. The differential of v would be equal to dx. So the antiderivative would allow us to say v is x itself. And checking that out, if v is equal to x, then certainly dv would have to be equal to dx, which is the correct upper value there. So our table is set up, and we can immediately say, then the antiderivative is this product first, x natural log x, minus the definite integral of this times this. But x times 1 over x tells us that the antiderivative is simply dx, or 1 times dx if you feels more comfortable to put some value inside there. So the antiderivative of dx, we've really already done it once, is x itself. So this is x natural log x minus x. And once again, for emphasis, if you've seen that enough times, it was in the book, we solved it in class 3 times so far, and you just state the antiderivative of this is x natural log x minus x, that would be completely fine. So we can take that as a given integral, much like antiderivative of sine, for example. So coming back over here, the result of that work tells us we can take the antiderivative of x for an x squared over 2 minus antiderivative of 1, which is just an x, minus the antiderivative of the natural log of x, which is x natural log x minus x. And here I really should have put a constant. I neglected it this time because we are doing a definite integral. But as a formula, that's probably the most appropriate thing to do. We'll evaluate from 1 to 3. Does that look all right to folks so far? It is kind of a mess. Another strategy you can take here before you do the evaluation and get many, many different terms is there's really no harm in simplifying first. So you could say area is x squared divided by 2. This is a negative x here. The distribution, however, will produce a positive x for immediate cancellation. So we can say negative x is gone. This turns into a positive x, which is gone, minus x natural log x, the sole survivors, from 1 to 3. Then I would probably evaluate at that step. We can now say, finally, the total area is input 3 to get 9 halves minus 3 natural log 3, then minus the result of inputting 1. That gives us a half here, minus 1 times natural log of 1. But we should always be ready to go in the back of our mind that natural log 1 must evaluate to 0. And in this one problem, it would be evident from the graph as well. So altogether, total area is 9 halves minus 3 natural log 3 plus 1 half. So finally, together that makes 8 halves, so we get a 4. The total area of that region is now 4 minus 3 natural log of 3. So we have the total area under the curve. It's master computation because typically in these types of problems, we wouldn't force an integration by parts. But I would take it as a nice general overall review problem. And it's worthy to mention you can take this as a formula on your note card if you'd like. And if you memorize this, you're always free to use that result. But questions so far with our first integral? Draw the chalk. Okay, let's go off to the next one. So we're 1/3 of the way done. We want next the x-coordinate of the centroid, or x bar. So x bar will be the reciprocal of area. This time area is kind of nasty, so I would only substitute in this value at, say, the very last step, so I don't have to write a whole bunch of stuff every single line. We'll take the definite integral as we go from 1 to 3, as before. So in all three integrals, it's always 1 to 3. But for the x-coordinate of the centroid, we take x multiplying this thing, x minus 1, minus the natural log of x. So that's the integral that we must solve. Sadly, we cannot use the work from before because before we find antiderivatives, we need to distribute x into the entire problem. So now we have that x bar is reciprocal of area, multiplying the definite integral from 1 to 3 of, now it's x squared minus x natural log x dx. So we're in pretty much the same position as we were before, where we could have said the antiderivative of the first one in our problem is just going to be x cubed divided by 3. Antiderivative of this one is just x squared divided by 2. But now we have a non-trivial antiderivative, x natural log x. And it keeps getting worse. But again, it is just good practice. So if you see things like this in the homework, I would take this chunk. We have to eventually solve x natural log x dx, antiderivative. So let's work that out once again. What would you say the technique is this time?
Same as last time, right?
Yeah, same exact technique. We'll do integration by parts. So that means select a u, select a dv, and there is some guidance on integration by parts, the so-called acronym LIATE, which says the best choice should be L, which stands for logarithms So if you did go with the x, it could work, but it's best to go with the natural log x. Since that's a logarithmic function and the differential of u is equal to natural log x, simplifies quite a bit to 1 over x. Then, if u is natural log x, dv this time has to be x dx. So it's very similar in spirit to what we've done before. Antiderivative this time for this thing will be x squared divided by 2. So now we're ready to express this integral to say that this will be equal to natural log x times x squared divided by 2. I'll write that as a half x squared natural log x minus the integral of this times this. First feature we have is a half, so I'd probably write the 1/2 on the outside. So I take care of this portion. Then it's 1 over x, oh, don't forget your dx. It's 1 over x dx times x squared, so that reduces to just x dx as an antiderivative. So, look all right to folks so far? Okay, so we solved this last antiderivative. Then we can go back to the x-coordinate of the centroid, and we have so far a half x squared, natural logarithm of x, minus antiderivative of x will be x squared multiplied by 1/2 again, plus a constant. So we could clean that up a bit, but we could also just input the result up in our new line. But how does that look to folks to that point? Does that appear all right so far? Okay, so if we take this stuff, keep in mind we're going to throw a negative sign in front of it, so we'll also have to distribute -1 at the same time. We now have x bar is equal to reciprocal of area, and we're doing line by line or term by term anti-differentiation. So starting with x squared, we're up to x cubed multiplying a third minus, for x, we have x squared multiplying a half. Then finally, x natural log x with a negative sign is the negative of this entire result that we worked out on the margin. So that would come out to -1/2 x squared natural logarithm of x. Then the negative sign distributes to here to give us positive 1/4 x squared. So plus 1/4 of x squared, and there is a constant of integration, but when we do the evaluation, it will always cancel. So we traditionally leave it off, and we'll be evaluating from 1 to 3. So we're about there. But once again, you can treat yourself to a bit of a simplification before the evaluation, which makes slightly less mess at the cost of an extra step. So it's a bit of a balance there. I'd probably combine a 4th x squared with -1/2 x squared, just to simplify it a bit before we get all those terms. So we can convert this by multiplying 2 over 2 to 2/4 -x squared. And now x bar is equal to reciprocal of area multiplying a third x cubed. These combine to -1/4 of x squared minus a half of x squared natural log x from 1 to 3. So let's work all that out. We're ready to finally evaluate that x-coordinate. So in the evaluation, we can say that x bar is equal to 1 over, the area itself is 4 minus 3 natural log 3.
Shouldn't it be 5 minus?
Oh, sorry, where at?
No, it should be 4.
Should be 5? Oh.
Oh yeah, this came out to, or hang on, 10/2, which is 5. What happened here? Oh, this should have been a -1/2, shouldn't it? There was really a minus there. Thanks for spotting that. It would have been 10/2, but it's really a minus. Somehow I did not distribute, or I simplified the fractions I must have. Something happened there. But does that look better, folks, so far? Okay, so distribute the negative here. It should have been -1/2, reducing that to a 4. So we can go back over here to say 4 minus 3, natural logarithm of 3, is the reciprocal of area, and it's going to multiply a whole bunch of stuff. So let's start with 3. 3 comes in, cube it to get a 27, divided by 3 produces a 9. So we're on our way. So 3 here gives us a 9/4 with no reduction. Minus here we have -1/2 of 9, let's call that 9/2, natural log 3. So that's the first portion, then we evaluate at 1. So I'll write minus Don't forget you have to distribute, so parentheses are necessary on that step. Inputting 1 will give us a third, minus a fourth. Then a 1 here, it does kill it off, so hey, we get 1 freebie, right? Natural log of 1 is 0. So there it all is. That is our x-coordinate of the centroid. That's pretty nasty. So as a problem, if this was on the exam, I'm sorry, but you could stop there. That would be an appropriate stopping point because the calculus really ends there. If I was doing it at the homework problem, I wouldn't be happy with it, but I would be tempted to get full credit on that problem to just put in the calculator to see what it comes out as. And when I did that, again, I could have made a mistake because this is a lot of stuff to put in a calculator. I found that x bar was equal to 2.45, putting all that stuff in the calculator. So if we go back over here, 2.45, well, this would be about 2.5, and it seems to jive. My point is probably further to the right than it needs to be, but keep in mind that's not a perfect hand-drawn sketch.
Did
Questions?
you miss a -1/2 over here?
Minus 1/2 on this right here?
Yeah.
I must have, let's see, we had, well, I inputted 3 right here to get the 9, and natural log 3. I must have just put the 9.
The one. When you input the 1, not the 3.
Oh, when I put the 1 inside this portion right here?
Yeah.
Well, the trouble with
Oh,
that is,
it was multiplied by, okay.
yeah, exactly, the natural log 1, that was our 1 freebie, who wipes it all out. Other questions with that so far? Okay, so 2/3 of the way done. We have the x-coordinate of the centroid. I think the major purpose of this problem is to show how interesting they could get, but also to discuss antiderivatives like, say, natural log x. You can rip through this problem really fast if you just happen to have that known by formula. So this is something you can always take as a given. This one, however, x natural log x, well, I think that's one we really ought to work out. I think once you do this enough, you'll see what the patterns ought to be. But it does take substantial work to express those things as a formula. But let's go off to y bar as our next portion. Any questions first? Questions or comments? Okay, so we're off to the last one. The second coordinate of the center of mass, or the centroid. Hopefully this will fit in the chalkboard. Is y bar equals, we take, once again, reciprocal of the area. We'll always be integrating from 1 to 3 on all 3 integrals. And this is the new change. We take a half, we're going to multiply it by the top curve squared. So we have to take x minus 1 and square that whole thing, minus the bottom curve squared, which was natural log x. And we have to be really careful writing that, because if you wrote it as natural log of x squared, that could be problematic. Would folks agree with that? It really causes an order of operations type issue, where if you write natural log x, the first thing that happens is you must evaluate the natural log of x. So if you want the natural log of x squared, you don't necessarily have to have the brackets, but the function notation for natural log of, with parentheses, x, is pretty important to communicate the right value. Add brackets just to be really sure we don't confuse what's being squared. Not x, but the natural log of x. So we take all of that, dx, and integrate. So it's going to be kind of the same pattern as before. We first can FOIL all this out to say it's reciprocal of the area, definite integral from 1 to 3. We could take a half and just join it with the area. So let's say 1 over 2a, just to simplify it. Now on the inside, x minus 1 squared gives us x squared minus 2x plus 1 minus the natural log of x squared dx. So the very next step is to go term by term anti-differentiation, where once again, there's no problem with the first 3 terms. That's ordinary calculus 1 material. That's the problem. We need the antiderivative this time of natural log of x squared. So let's work that out on the margin so we don't carry that huge thing. We have to decide on something to delete. How about total area? Let's save this result. Is that all right to folks? Okay, let's kill off the total area integral so we can work in a pretend margin to solve the antiderivative of natural log of x squared. I don't think we've seen anything quite like this one. We may have. It's been a while. What would you folks say the method ought to be for that thing? Did I hear parts? Yeah, it's integration by parts again. So let's do parts. So we can say u. Here, this is kind of strange. For the u, I would just grab just about everything. Let's take the entire natural log of x squared and hope for the best. Then dv has nothing to take but dx. The reason I took everything there is if I broke this up and said u is natural log x, I would have to say dv is natural log x dx. We do know the solution to that has an antiderivative, but this is starting to get really complicated if we went down that line. Solvable, but on lots of steps. So what's interesting about this one is it suffices to take the entire logarithm function to whatever power it happened to be. Then we take the differential of this equation here. So chain rules first says we do the derivative of the squaring function. Power 2 comes down, multiplies the natural log of x. So now it's a power 1. What would be the rest of it? It's been a while for chain rule 2, hasn't it? That makes these really good problems. Good chance to review and sharpen skills. But there's really two functions there. We have the squaring function, x squared. So what would be the other function?
1 over x?
Sorry, say again?
Is it 1 over x?
Yeah, the inner function is natural log x, and that's our next derivative to take. We multiply by the chain rule the derivative of natural log x, which is, as you said, 1 over x. So that'd be the full differential, and don't forget, as I tend to do, dx on there, since it is a differential equation now. Then antiderivative of this, we've done twice now today, is x. So that's our full table. Now we can come back and say this will be equal to u times v. So it's x natural log of x squared minus the integral of this times this. So we have a constant of 2 on the outside between these two portions. So we can make it 2 there. Then we have x times, or 1 over x times x. So there's a cancellation of this to this. All that's left is natural log of x and the dx. Does that make sense so far? So we pulled the 2 out of the antiderivative. 1 over x with x have canceled. There was just natural log x to the power 1, so I just wrote natural log x. But once again, that is an antiderivative that we can just grab and use. So we don't have to do integration by parts again on this one. That'd be horrible. We can just say that the answer is x natural log of x squared minus twice the result of that as an antiderivative, x natural log x minus x. So x natural log of x minus x. Then there's truly a constant of integration there, but we'll throw it away in the evaluation. So I think that's about all we could do with that. If you'd like, you could distribute the negative 2 in to say it's x natural log of x squared minus 2x natural log x plus 2x plus a constant. So let's take that and throw it back into our problem. Any questions so far to that step? Okay, so back in our original problem, keep in mind we're going to need to think of this as all being associated due to the negative in front of that natural log x squared. So now we have 1 over twice area, and let's put in here, how about a parenthesis, and we're going term by term now. So this is the fun part. Here we get x cubed thirds minus, here it would be just an ordinary x squared, because the derivative of x squared would produce the 2x with the negative sign. We throw in the negative there. Then plus x. Now for here, we're taking negative and distribute it into all of these terms. Now we're going to drop the constant c due to the evaluation, causing it to cancel. So negate all those terms and we'll get minus x natural log x plus 2x natural log x. Oh, that's x natural log x squared. Let me try again. Just wondering why we didn't combine those. So x natural log x squared minus 2x natural log x plus 2x. Evaluate all of that. This almost looks like punishment from 3 to 1. But keep in mind, once you do the evaluation, the calculus has ended, and you can stop there if you like. especially on exams, you'd be practically encouraged to, just so that you can move on to the next problems. But any questions to that step so far? Okay, so if this was a homework problem, this is probably where I would stop so that I can study more calculus and do more homework problems. I'd go 1/2, total area we saved is 4 minus 3 natural log 3. And it's going to multiply a whole bunch of stuff. First, evaluate at 3. We once again will get a 27, divide by 3, so a 9. Minus 9, so hey, there's already a cancellation. It's not as horrible as it looks. Then put a 3 there. 3 goes there, so minus 3 natural log of 3 squared. Then over here we get minus 2 times 3, so 6 natural log of 3 plus 6. So that's the evaluation at 3, and I'm not sure if I'm going to have enough space, but let's try this. Minus, now we're doing it at 1. When we input 1, this would go away due to the natural log 1 wiping out everything. Natural log 1 here would be a 0, wipes out everything there. So we would just get the remaining 4 terms. So I have a third, minus 1 plus 1, so another cancellation, then way out here, plus 2. So that would be the full evaluation of that whole thing. Then if you really want to check your work, carefully simplify it, put it into the calculator, and you might find, I mean, I could have messed this up, this is a lot of stuff. Y bar is approximately equal to 1.16 was the result I got. So if you did do that step, you can now have the benefit of coming back up here and see if it makes sense. We're a bit off by the hand-drawn sketch, but I would say close enough. I feel about all right with that. I should be a little bit lower. I think we said it should be a slightly bit to the left, or possibly the only thing that needed to adjust is a better hand-drawn sketch. But we did it. That's what a hard problem would look like. Problem number 31 is kind of the average between the two problems we did. Not quite as bad as this, but it's a little bit more difficult than the first one. Questions so far about centers of mass? Okay, so now you can build really cool tables or plates and balance them if you really want to. People do that all the time on the beach with rocks. It's rather cool. So you have an upper hand now on stacking rocks or something like that. But the next thing we want to do is go to chapter 9, where we'll be looking at differential equations. The questions you might have is, why are we doing differential equations when there's an entire class called differential equations? There's kind of two answers. One answer is a lot of people that could be taking physics and engineering may already be looking at differential equations as we speak. Another reason is you could take differential equations as being probably the major application of integration for this entire course. Chapter 8 has some great stuff, but I would say chapter 9 is even more important. We're not covering all of chapter 9 due to issues of time. So the sections we will cover are the introductory section. 9.2 has a lot of work on graphing, which is quite important and interesting, but a good differential equations course will hit that section really hard. So we're going to skip it for the sake of saving time. Then here we'll solve separable differential equations, and 9.5 will solve linear differential equations. So let's see what differential equations are and solve the first couple classes of interesting ones. Any questions so far before we start? I think we have a good 9 minutes. How about we start with just a problem that we can do a quick computation with and then come back and finish up on Wednesday, federal holiday next Monday. Does that sound all right to folks? Okay, so let's write down a differential equation. We're going to write down a supposed solution, but we'll check if it really is one. So this is section 9.1, which is, I'm not sure what it's titled yet, Modeling with Differential Equations. So first, let's just write down a differential equation. So it says that consider the equation, we should say differential equation just to be explicit, but that ought to be in the context. It should be a differential equation. The differential equation that we have is y double prime minus y equals 0. So that's our good old differential equation. So there can be many, many solutions to this differential equation. What's new when we go to differential equations is that the solution to an equation like this is very, very different than a solution to an equation that looks like, say, something along those lines. Ordinary algebraic equation has a solution that would be a real number. X would be 5/2. However, in a differential equation, the features are we're taking the second derivative of some function minus that same function, and we want to balance that equals to 0. So the solution is some function. Let's not say the solution because there are many. So let's say L solution is some function y is equal to f of x that is second, or that has a second derivative. So as soon as you find a function that does have a second derivative that exists, and take that second derivative minus itself, if it balances to 0, you've found a solution. The trouble is we want to find all solutions, and there are many, but we're going to start with just finding a particular solution. If you look at the form of that thing, second derivative of a function minus a function, anyone happen to know a solution to that?
Would you just like add y to the other side and then take the antiderivative twice?
You could, but the trouble with that is we wouldn't know what we would be taking an antiderivative of. Say, for example, if we go y double prime is equal to y, this is a good approach, and we can say that this is y double prime dx, if the independent variable is x, is equal to the antiderivative of y dx, but we'd be essentially stuck at that step until we knew what we were in fact integrating. But that's a good idea because that is in fact the heart of the technique in section 9.3. We try to separate things out and integrate. But questions so far about that? Okay, so we still have to try to find a function. When we go to section 9.5, we'll say, of course, I know exactly what the total solution is, but we're getting there. And this is one where we can come up with a function and check it. Anyone have a particular guess to try? Well, this is what we could try. So let's check one function that may or may not work, and then we'll check another one. So let's say for our part A, is y equals e to the x a solution to this equation? And by this equation, I mean that one. So in order to do a check on the solution, well, if it was an ordinary algebraic equation, you take the value of x, throw it into the original equation. For differential equations, it's not any different. I need to take the value of the second derivative, throw in the function, and see if it balances to 0. So the work in doing a check would be take y prime, which is e to the x. That's a fantastic function, right? Just do it again, y double prime, still e to the x. Any order derivative you like, it's always e to the x. That means y double prime minus y equals 0 would be e to the x minus e to the x, which is 0. So we get something that balances to 0 equals 0. So what would you say the end assessment is to this? Is y equals e to the x a solution or a non-solution? Some people like it. Yeah, I agree. If we took the second derivative, plugged it here, took the function, plugged it there, and it balanced to 0, it means, yeah, we found a solution. That's wonderful. This shows y equals e to the x is a solution. Tragically, there are many, many solutions, but that's okay. That's a start. Any questions with that so far? Okay, maybe one last part, and then we'll call it a day. Let's grab some other function. Let's say, for example, for part B, is y equals natural log x, a solution. By a solution, we mean a solution to that same equation once again. So this time we have to go through the same sort of work. We take the derivative of natural log x. So y prime would be 1 over x, or if you prefer, x to the power negative 1. Then the second derivative is the derivative of this, which is the negative of x to the power negative 2, or if you prefer, negative 1 over x squared. So I have the first and second derivative, but all I need in my equation to check if it's a solution is second derivative and first derivative. So we go back to the original format of the differential equation. We have that y double prime minus y equals 0 would be negative 1 over x squared minus the natural log of x, which is 0. But the tragic thing about this is that may hold for specific values of x, but it must hold for all values of x. We must say that that's not equal in that equation. So our assessment this time is, what do we get to say about y is equal to the natural log of x?
Not a solution.
Correct. We do not have a solution here to that differential equation. So y equals natural log x is not a solution, sadly. But it is what it is. And I think that's a good initial overview of chapter 9, what we'll be doing. We'll be taking equations and trying to find all solutions. It's also equally important to be able to test whether your solutions are actually solutions or non-solutions, as we've just done. I think this is a decent stopping point. If you have questions, feel free to stick around. And keep in mind, next week we'll come back on a Wednesday due to the holiday.